Thank you very much. It's a pleasure to be back here. So I'm Oleg Eyser. I'm a scientist at Brookhaven just down the road, and I just learned that unfortunately are not going to visit while you're here, but I hope many of you have seen it, and I'm going to show a few pictures also about on site. I think if there are questions throughout, I'd be happy to just answer them when they come up, so we avoid any confusion or misleading throughout the talk, and then we could just afterwards. So I'm going to talk about hadron polarimetry, and that's mostly proton polarimetry. And what that means is actually we want to measure polarization, and particularly the beam polarization, either at the relativistic heavy ion collider or other accelerators, or the electron ion collider at some point in the future. And this is specifically talking about the proton beams, in addition to what Cyprian told you, I think it was yesterday or the day before, about the electron beams. So before we start there, I think we should clarify what we actually mean with polarization. And polarization is not necessarily something bad, like in politics at the moment and in most situations. So if you look this up at Merriam-Webster, what we mean by polarization is actually referring to the magnetization of things. So it's an instance of magnetizing, or the state of being magnetized, to the degree to which a body is magnetized, so oriented along the external magnetic field. If we talk about particle beams or ensembles of particles, polarization is really defined as the average alignment of the magnetic moment of this ensemble of particles with respect to this external magnetic field. So if we have a particle that has a spin 1/2, the polarization is really the normalized difference of the particles with the spin along the magnetic field minus the spin anti-parallel to the magnetic field divided by the sum of this. So the polarization in that case can have a value anywhere between -1 and +1. So if everything's along the magnetic field, it's +1. If everything's opposite to the magnetic field, it's -1. And that's something that you should actually be careful about when you talk about spin physics and polarized physics in general, because most people just mix the two and use them interchangeably, where they talk about the polarization of a single particle or the spin of the colliding particles or something like that. So when we talk about an ensemble of particles, we should always talk about the polarization. If we talk about a single particle, we should talk about the spin of the particle. So a general outline, I'm just going to briefly talk about a little bit about the motivation for the polarized electron ion collider. I think you've got plenty of other talks, whether that's with Hamiltonians or without, that talk about the physics itself. We're going to keep that short. And then for the remainder of today, I'm going to talk about polarized particle beams and really motivate why we actually need to measure the beam polarization. And then tomorrow, I'm going to really talk about the polarimetry itself, and then conclude with an outlook for the electron ion collider in summary. So just one slide about the motivation. As I said, you have plenty of talks in these 2 weeks about this. You can look at all these documents, and really the core part for the polarimetry is that in one of these main topics, it comes up that spin and polarization is an intrinsic part of the electron ion collider, where we want to measure the distribution of spins or the polarization of quarks and nucleons, and potential correlations with transverse momentum in the nucleon. So I think the real starting point that everyone should have either on their laptop or a printed out version is this white paper, which at this point is actually 11 years old already, which outlines the physics overall. And then you've got these updates, the Academy of Sciences report, and also the yellow report for the detector design, and the two detector proposals, the ETCH and the Athena proposal, which have now merged into this EPIC proposal. And I guess a lot of you already work on this, so I would really like to refer you to the wiki page if you're interested in more details on that. So a different view of the electron ion collider here, so that you've seen this in various instances, the numbers here. So we talk about a variable center of mass energy in the range of 20 to 140 GeV. We have ion beams, protons here, helium-3, and then heavy ions, and then very important is high luminosity up to 10 to the 34 per square centimeter in second. And then usually what's thrown in there is just this, oh, we need the polarized electrons and proton beams with beam polarizations around 70%. So we're good to go and we can work with this. And that's actually not so easy, as we will see. And all this will then lead to the collisions at this detector location for EPIC now, and possibly the second detector at IP8. So this is all based on the current layout of the relativistic heavy ion collider. So this is an aerial view here, how this looks currently on site. This would be the ring here, and we have the two experiments. One is star that sits right here, the 6 o'clock location, and now brand new is Phoenix at the 8 o'clock location. So for the EIC, one of the two hadron rings will be kept. That's what we call the yellow ring, and then we will add this electron ring, which is the blue, the dark blue in this case, and we have the collision points at IP6 and IP8, and then we will also add the polarimeters or the polarimetry devices, which are currently planned at IP4, and then also around the detector locations. And I'm going to tell you why in a little bit. So, as I said, this number just comes up and it looks like it's not a problem, but really what you should think about is you have the colliding protons and electrons, and they come in bunches, right? So we have proton bunches, electron bunches. They have a specific size. They have in longitudinal and transverse direction. They have an intensity, and they have a polarization. And then also for the different experiments that we want to do, the electrons are typically polarized longitudinally along the beam direction, the beam momentum. And for the protons, we are interested in longitudinal polarization, but also in transverse polarization. And then we have electrons to get to these center of mass energies. We have electrons between 5 and 18 GeV in different discrete steps of 5, 10, and 18, and protons between 50 and 275 GeV, so 50, 100, and 275 GeV. To really get this variable center of mass range. But if you look at, you really have to think about how you get this information out and how you get this precision that you need. So in terms of the precision that we need, why do we actually need this high polarization? So this goes back to the figure of merit and the experiment that we want to carry out and how effectively we can actually do this. So let's take a very general physics observable interest here. I'm just picking one that's the polarized parton distribution function as a function of this partonic momentum x. It could be anything that's in some ways polarization dependent. So the cross section of this physics observable is essentially the same as the polarization itself. When we defined it, it's the normalized difference of these two different polarization states, the cross sections of it normalized by the sum of the two. So we want to carry out two experiments, one where the polarization is positive and one where the polarization is negative, if we only have two different polarization states, right? So in the experiment, we have this differential cross section, and I'm making this again pretty easy here. It's only a function of my detector acceptance. That could be the azimuthal angle, the polar angle. It could be differential in other variables, PT or other things. So I have this differential cross section with my detector, and then I have the collision luminosity, which essentially is the intensity or the amount of particles or the number of particles that collide. And I run my experiment over a certain time in this detector region, and I just do a counting experiment, right? So what I then measure is the number of events with positive polarization minus the number of events with negative polarization. I call this my asymmetry. So this is if my polarization of the colliding particles is 100%. So everything in my positive polarization, really, every particle in my bunch has the same spin direction, plus or minus. Now we put in the polarization where we know that not everything is necessarily aligned with my external magnetic field. So this polarization then scales my measured asymmetry by this value P, which is the polarization. And note, I already made an assumption here that we probably come back to later, where the assumption is that my positive polarization is the absolute value of the positive polarization is the same as the absolute value of the negative polarization. That doesn't necessarily have to be the case, right? So now I want to determine or calculate the statistical uncertainty here of my physics observable, and that's proportional to just the statistical uncertainty of my measured asymmetry scaled with the polarization. So if I assume Poisson distribution, my statistical uncertainty is just the square root of n. In this case, it's going to be a little more complicated with the error propagation, but it's in first order, it's just the square root of the total number of events there. So my figure of merit at the end of the day really is proportional to the number of events times p squared now. So that tells me if my polarization is 10% smaller than I would like it to be, I would have to run my experiment by twice that 10% or squared those 10% loss, right? So every percent that I lose in my beam polarization costs me money right away because I need to run my experiment for longer to get the same statistical precision. So the higher the higher the beam polarization, the easier I get out my physics. And that's why we use the 70%, because that's a reasonable number that we think we can achieve. And it's still within the range of being affordable. So back to my electron ion collider in this case, or Rick, if you want to think about this for the current setup. So we have the electrons between 5 and 18 GeV and the protons between 50 and 270 GeV, and we just want them to be polarized. That's a nice thought. The protons actually come out of the polarized proton or ion source here. And the energy with which they come out used to be on the order of 10 keV, now it's 35 keV, but we somehow have to get to up to 50 or 275 GeV. So there's a lot of work that we need to do in between with the booster, the AGS, and then really maybe 10-minute long acceleration from 20 GeV to 275 GeV. So there's a lot that can go wrong and happen to the particle beams during that time, which also could mean that whatever polarization we get out of the source might get lost, right? So I'm going to talk a little more about polarized high energy particle beams. And yes, well, there's a question in there.
Yeah, just a question on slide 7 where you showed the asymmetry equation.
This one.
Yeah, the other one on the left there. Yeah, so we aim at high polarization of 7%. Then we saw even yesterday that the asymmetry is proportional to the polarization, right?
Yes.
Yeah, but then do we have to care about the constant of proportionality? Or is it necessary?
Well, in this case, you don't really have to care about it. The only reason why you care about it is because, like I said, you want to be efficient in the way that your experiment works. Whether your polarization is 30% or 70% doesn't really matter for the asymmetry that you measure, other than that your relative significance is going to be smaller. So there's another requirement in there that the beam polarization should be known to less than 1% relative. And that's the important thing, is the 1% relative. So the uncertainty with which I need to measure my beam polarization should be 1% delta P over P. So if my beam polarization is 70%, I can get away with 0.7% uncertainty. If my beam polarization is 30%, I need to measure that beam polarization to 0.3%, right? But for the physics observable, if I have the time and money to spend on running my experiment, the value of P doesn't really matter that much. I mean, if it's 1%, you're gonna have to run 10,000 times as long. So you don't want to do that. But whether it's 50 or 70% is a factor of 2. Did that answer the question, or did I misunderstand it?
Yeah, probably maybe you could also comment on the uncertainty of the polarization. Usually at rig, I think it used to be 1.5%. So yeah.
Yes, it used to be, I'm gonna show something later. It used to be 4%, 3.5% for a long time. And in the last few years, it came down to 1.4, 1.5.
So for the AIC, we maintain the same.
Well, there's work to do still. We need to get that below 1%. Or on the order of 1%.
I have a related question. So if you go to the next slide, so there is a source, ion source, polarized ion source, and how do you make sure that these protons will be polarized along the way?
I'm going to talk about this on the next 20 slides or so. So that's the major part of the rest of these 45 minutes now. So I'm going to talk about this, but it would act right now. It would be nice if all the lights were out. So I'm going to start way back in the dark. No, you don't have to switch it off. It's just for this one slide. So I'm going to talk about the dark ages here a little bit. So I don't know if you know what this is. If not, I'm going to tell you it's the spectrum of atomic hydrogen. So we have the spectral lines here that started the whole mess that we're actually going to talk about, and that led to everything related to QCD, spin, and quantization. So the spectral lines of atomic hydrogen are actually were actually first explained by this empirical Rydberg formula, where you have the main quantum numbers n, and this Rydberg constant, and you have the inverse of the wavelength of these spectral lines, and you have this naive, which then led to this naive planetary Bohr model of the hydrogen atom. And you can see that you have different transitions here between these major quantum numbers, and you have the red line here, 650, and then the blue going into the ultraviolet 480, 434, and 410 nanometers. And you just have this empirical description and the different energy levels where you have the transitions between the two, between these different energy levels, right? So if you put this hydrogen atom in a magnetic field now, what you observe is a splitting of these spectral lines, which are explained by splitting of the energy levels, which introduce this orbital angular momentum. So for each major quantum number n, you have 2 times L, you have 2 times L plus 1 splittings of this energy levels. So for L equals 1 or n equals 1, you have the different possibilities of L being -1, 0, and +1. If n would be 0, you could have -1/2 and +1/2, and so forth. So you would observe the splitting of these spectral lines, and then try to deduce the splitting of your energy levels. And this really goes back to the magnetic moment that's related to this orbital angular momentum, which tries to minimize the potential energy in this external magnetic field. Where you have the magnetic moment, your magnetic quantum number, and the external magnetic field. If and even for that n1 level, like I just said, you observe two different splittings, -1/2 and +1/2, which is called this fine splitting, and that actually points to the fact that the electron has an intrinsic orbital momentum called the spin, right? So the spin is 1/2, so the orientation can be +1/2 and -1/2. And also there's a magnetic moment. If you look much finer, you can find out that there's a magnetic moment of the nucleus, which is suppressed by a factor of the mass ratio. So it's 2,000 times smaller than the electron. And that's what we call the hyperfine structure. So if you put your atomic hydrogen into this external magnetic field in the ground state, you will find that the energy level splits up into actually 4 different levels, which have this MJ plus 1/2 or minus 1/2, and then you have the nucleus with a proton magnetic moment plus 1/2, minus 1/2, minus 1/2, plus 1/2. So if you ramp up your magnetic field high enough, you can actually separate these energy levels and try to polarize your atomic hydrogen. So this was first observed over 100 years ago at this point by Stern and Geller in this experiment that they set up. So they had an oven that produced this ray of silver atoms. So it's not very well focused, but they send this through a non-uniform magnetic field. And as I said before, the external magnetic moment tries to minimize the potential energy here. And if this external magnetic field is actually inhomogeneous, it means that there's an external force that tries to pull the particles with an up spin in one direction with a minus up spin in the other direction. So you can actually see that at the end of this external magnetic field, the 2 spin states are actually separated. Now this looks very nice because you see this kind of eye-shaped picture here. In their original setup, it doesn't look quite as nice because, as I said, this is just an oven that produces these silver atoms. So they actually didn't see these 2 lines. They really had this kind of eye-shaped thing, but it was pretty much filled on the inside too. But they were actually able to show that the electron spin is 1/2 h bar because they had these 2 different lines on their photoplate at the end of the day. Now, the nice thing about this is that you can use this to really spin polarize your, in this case, the silver atom beam, polarize it with respect to your electron spin. And if you go back to the atomic hydrogen, where we have these 4 states, you could come up with a device where you use 3 different steps to really polarize the proton or the nucleus of your atomic hydrogen, right? So in the first step, because this the magnetic moment of the electron is much larger, you have your first setup of your Stern-Gerlach experiment where you separate with respect to this MJ. So you put a block here, say, at the end of your magnetic field, and you only let the states 1 and 2 through, and then you can use what's called a radio frequency transition, where you essentially use an electromagnetic wave of the exact right wavelength or energy to induce a transition here between states 2 and 4. So you essentially flip to transfer the polarized electron, the polarized electron spin onto the nucleon itself. So in this case, you have the electron spin in this case is again unpolarized, and the nucleon's spin is polarized. And then you have a second setup of your Stern-Gerlach setup where you again separate the 2 states with respect to the electron spin. You block out the one that you don't want, and what you end up with is a state where the electron is polarized and the nucleon, or the proton in this case, is polarized. And this is what you want to work with to get at the proton. Now that might sound easy enough, but the problem is this one's still an atomic hydrogen atom, atomic hydrogen, right? So it's neutral, so you can't really use that to create your particle beam. So in real life, it looks a little more complicated because you need to somehow ionize this atomic hydrogen, so you can use an electric field to accelerate a little bit, Then you try a different setup here to induce the polarization on your electron, transfer that to the proton itself. And then you can use this charged proton beam with electric fields to really get it out of the source. So this is a very complicated thing, and this is a paper from 2011, which in great detail explains how this works at RIC at the moment. This is the most advanced polarized proton source in the world. It's called this optically pumped polarized ion source, OPUS, at RIC, and it creates beam bunches, proton bunches of about 0.5 to 1 milliamps in a bunch that's about 300 microseconds long, and the beam polarization out of the source is 80%. So that's what we get to work with. And I'm referring to RIC here, but it's going to be essentially the same for EIC, right? So one proton bunch in RIC or EIC has this intensity, this current in it, and the beam polarization is about 80, maybe 85%. So now you need to get from 35 kV to 50, 100, or 275 GeV, and try to keep this 80% at least 70%. So you've got about 10% to work with that you can afford to lose. So now on the next few slides, I'm going to talk a little more about the details of the particle beam optics. And I don't know how much talked about this in his slides about the basics themselves. I want to point out a few things here before we come back to the polarization itself. So we want to have a circular accelerator or circular storage ring, because that's really nice to put an experiment in, right? Because if we have particle bunches and they collide, not every particle in that bunch will do something, right? So if the particle comes back, we can use it at the next turn and try to use it again. So it's a very efficient way of doing things. Also, we have an acceleration device here, an RF unit, which allows us to use it at every turn. So we don't need to spend so much money on the acceleration device itself, because we can use it a few thousand times from injection to our flat top, because it comes around in circles. Now the drawback is that we're going to need dipole magnets. So we have the charged particle beams. We need a dipole magnet to keep the particles on our circular track. And we can potentially also use other magnets like quadrupole magnets or 6-pole magnets to focus the beam in one or the other direction to really make the best of the phase space or the emittance that we have at the location of the experiment. Now, this assumes a few things to get started. So we need to keep the particles on a circle, which means that there is a closed orbit. So every time the particle comes by here at one location, it should be either near that same location or in that same location. The beam, when it comes in here, as we said before, is in the form of a particle bunch. So the beam has a certain size and longitudinal transverse dimensions, and it potentially also has a spread in the momentum distribution itself. So if the momentum distribution is not just a Green's function, that they're not all at the same momentum, it has a different width, a specific width, it means that the particles will start to oscillate around this closed orbit. And I tried to illustrate this here. Actually, someone tried to illustrate it. I just copied it. It means that this size and the momentum spread means that the particles will actually oscillate around this closed orbit. That's called the betatron oscillations. And this red line essentially just shows you the envelope of the space that's being used up by the beam. So a particle that is close to the edge at this element will come down here and be close to the other edge at this element, and it oscillates in this way. A particle that's close, that starts in the middle here, might follow this path. So the oscillations of single particles are all different, but they all stay within this envelope, right? And that's called what Todd also talked about, this photo or F0D0 lattice, which describes the orbit envelope itself. This one's called the beam optics because it essentially goes back to Liouville's theorem. The phase space of this phase ellipse and the emittance of the beam itself are invariant. So whatever I use for quadrupole or sexpole magnets means I can squeeze my beam size in one direction to increase my luminosity at the experiments, maybe a little bit. But at the same time, when I do that, it spreads out in the other direction. So I can try to squeeze it in different ways, but I can't make that phase ellipse really smaller by doing that, same way as it applies in optics. So why is this important to begin with? Well, the problem is that if we have these betatron oscillations and we have this periodicity in our machine, if there's anything wrong with how we place the magnets, how the magnetic field really looks in real life compared to what it should be ideally, it means that any of these mistakes can lead to resonances and make the beam unstable. And resonances and beam instability, if you think about this as being a fairly small accelerator, a few hundred meters, but even for Rick, it means that every mistake that you do, for example, in this blue magnet, you do that mistake 10,000 times a second. So even the smallest mistake can immediately blow up the beam, and within 1 second, the beam is essentially gone. So what you need to do is you need to avoid these resonances and unstable points, and that refers back to these betatron oscillations. If these in different dimensions, x and z in this case, if these combined are integer numbers, you will touch on these resonances and your beam becomes unstable. So that's illustrated in this figure here. We have qx and qz, and the different resonances in first, second, and third order in this case. And then you try to find a working point that sits as far away as possible from all of these lines to make this stable. Now, if we throw in the beam polarization or the spin, the magnetic moments, you had another complication which has the same source, which is the periodicity of your setup and the magnetic fields that interact with the magnetic moment of the particles, which is related to your spin polarization. So the all of these magnets, the dipoles, the quadrupoles, the six poles, they all result in a precession of your spin direction, of your polarization direction around this external magnetic field. And again, if there's something wrong in your setup, if there's something wrong in your magnetic field, every time the particle comes by, it does the same mistake. So it can lead to rapid depolarization. And there are different conditions here. One is related to the transverse magnetic field, and one is related to the parallel or longitudinal magnetic field, which affect the precession in different ways. And if either of these hits an integer value, you hit a resonance that you really want to try to avoid. So this is very nicely described in this original paper here by Thomas and then Bachmann, Michel, and CTEQ. So this is generally called the Thomas BMT equation. And you can see different things here. So this is for protons. So the gyromagnetic number is 1.79. And you see different things here. So you see the gamma factor, you see the G factor here, and the external magnetic fields. This is just a spin, and then it goes with 1 over the charge over the mass. But the important thing is the G gamma here and the 1 plus G in front of this, which means that for different conditions, we have these so-called intrinsic resonances, which is the gamma G factor here. If this one's an integer number, we hit a resonance, and then we have intrinsic resonances, which essentially relate to this part here. It's just the gamma G there. If this is an integer number, we potentially hit these imperfection resonances. So the intrinsic resonances is something you can't really do anything about it. The imperfection resonances, you can potentially do something about it if you try to be more perfect, obviously. But whatever you do, you will always find them. So now the important thing here is this gamma factor in front of the two, which means that if we again go back to the RIC source, 35 kV, and you want to go up to 50 GeV or more, this gamma starts at close to 0 and it ends up at 50 or at 275 or more. So you're going to hit 100 or 200 of these resonances that you have to deal with during your acceleration from the source to the flat top energy that you want to work with. So I'm going to show this example, the Kula synchrotron at COSY, which is actually where I started my work many years ago. And it's a very nice accelerator, a storage ring really, which has a maximum momentum of polarized protons of 3.3 GeV. So it's fairly small, but it's actually a very sophisticated machine itself because it has this cooling capability and the polarization itself. So it's actually being used for a lot of high precision experiments these days. So we have the injection here. We have the elements that I talked about before. Let me see. We have the where to go? Where's my RF unit? So we have the different experiments here. We have the dipole magnets here. We have the cooling here, which is not important for this case, but we have the quadrupoles here. And then we have the RF unit here. And that, excuse me. So the injection is at about 500 MeV proton momentum, and the flat top energy is at around 3,300 MeV. So it's a fairly small range, right? An energy that you have to cover here, but you can nicely see the problems that we talked about before. We have the intrinsic resonances, which are the green ones, which I actually didn't mention this on the previous one. It also has this P in here. That's just a number. It's called the super periodicity. It's a number that's specific to the machine that you're using. So it essentially reflects the geometry of the setup. So for RIC, that's 2, and I think for COSY it was 6. So these intrinsic resonances actually go slightly tilted through as a function of the beam momentum, and the imperfection resonances are actually fixed in energy, right? So we have gamma G1, 2, 3, 4, 5. And for the intrinsic, we have these different combinations where we have the working point of the spin or the spin tune, where you have these functional form. So we have about 12 resonances that we have to cross for COSY. And you can also see something. So the black line here is what's called the working point or the spin tune itself. And you can see for the intrinsic resonances, there's something you can do. You can change the working point pretty quickly by using these air quadrupoles. So they're just quadrupole setups without any iron in it. So they're very fast. And you do this to minimize to maximize the crossing speed of your intrinsic resonances, right? So you try to make the black line and the green line essentially perpendicular. It doesn't help you with the imperfection resonances. And then the nice thing about COSY actually was that there was a way to measure the beam polarization during the ramp itself, during the acceleration, not in just one measurement, but so that the machine itself was able to re-inject the beam every few seconds automatically, ramp the protons up to flat top, dump it, and do that again. So you could run this thing automatically, and you could make this polarization measurement and then just average this over many days or weeks, and you could measure the beam polarization throughout the acceleration itself. And there's one thing that you see here that you can also see at RIC, and that will be used at the EIC, is at injection, your polarization that comes out of the source is positive. And then you hit this one resonance, which is very strong. And instead of trying to minimize the time that you're close to this resonance, you actually try to stay as long as possible there to induce a complete spin flip or polarization flip. So in this resonance region, you flip the polarization, you accelerate further, you flip it again, you accelerate it up here, you flip it again. So the polarization comes out of the source as positive, and at flat top, the polarization is actually negative. That's something that's being used for a lot of strong resonances at RIC. And you have to make sure that you understand where this happens in the acceleration, so you actually use the right value for your mean polarization, right? So for RIC, that's more complicated, obviously. So this is from the configuration manual from 2004. This is an in paper. You can find this online. We have the two experiments here. We have what we call the blue and the yellow beam here, comes out of the source, and the AGS goes in here. And then you have those two crossing points, and also what's included here, what we call the spin rotators, which is something that we use to, so the stable polarization direction in the machine is transverse. So if this is in the plane here, the stable polarization direction is transverse to the accelerator plane. So if we want to measure helicity asymmetries in the experiment, we need to have a spin rotator, a polarization rotator that rotates the polarization from vertical into longitudinal for the experiment. And then right afterwards rotates it back, because otherwise we would lose the polarization in the dipoles that follow in this sector here. So similar to what I showed for COSY, this is how this looks for RIC, right? So we have the imperfection resonances, they're green now, and the intrinsic resonances are blue and not red anymore, but same statement here, gamma G for the imperfection resonances, and then this super periodicity, nice word, for the intrinsic resonances. And this shows you really the strength of the resonances for the imperfection resonances and the strength of the resonances for the intrinsic resonances. And this one goes up to 250 GeV, which was the current maximum energy for RIC. So it's going to be expanded by another 25 for the IC here. But you can see the imperfection resonances actually start fairly small. And then the higher you go in energy, the stronger they get. And then for the intrinsic resonances, there are quite as many, but you see that there's actually not really good pattern how strong they are related to the energy, but some of them are really much stronger than the imperfection resonances. So overall, you're dealing with a few hundred of these resonances that you have to cross. Now, one thing that you can also do, like I said, for the intrinsic resonances, every time you come by the same point and you give your particle the wrong kick for the spin or the polarization direction, there might be something that you could do, and that's called a Siberian snake. So the Siberian snake, they're different versions, they're full and half snakes. What they essentially do is they advance your precession by either a half or a fraction thereof. So when they come into this, when the particles come into this snake, the polarization might point up. It goes through this wild roller coaster road, and at the end of the snake, the polarization points down. Which means if I have something here that creates that really causes my intrinsic resonance, in one turn, it gives me a kick in one direction, and then it goes around and it flips it from down back to up. And it means in this case, it gives me a kick in the other direction. So there's something you can do to deal with these intrinsic resonances to really mitigate them or reduce the strength. Now, these devices are essentially dipole magnets in a very complicated setup, So this is a picture of how this strong snake in the AGS was constructed, and you could see the winding here. It's a very complicated thing because you have to make sure that you're at every point in this roller coaster ride, you have the right magnetic field to get the particle, keep the particle on that track that you wanted to keep it on, right? So this is maybe a little more instructive. It has a lot more information also, but you can see on the left side here, as a function of the Z direction, that's the beam direction, and you have these 4 different sections in your snake that's symmetrical around the center point. This is essentially the polarization direction, and you can see you come in here with a positive vertical direction, that's SY. SZ and SX are 0. And then you turn this positive SY into a negative SY. If your magnetic fields are a bit off, you might just only come out to here or there. So you really have to make sure that you understand what you're doing. But at the same time, you have this roller coaster ride. This is just the transverse direction in X and Y as a function of Z. And you can see it goes kind of like this, but it comes in at the center of the beam line and it goes out at the center of the beam line. So that's important. And this is just the magnetic field itself, the field strength that you need to create inside of the snake. So for brick itself, this is an attempt to do the measurement that I showed you for COSY. It's obviously more complicated because each acceleration takes about 10 minutes from 25 GeV to 250 GeV. So you can't just do this automatic COSY scan that you do every few seconds. And then also the polarimeters take a lot longer to give you a good measurement, but you can see different. So what was done in this case was we used different flat top energies to measure the polarization essentially across this acceleration cycle. And you can see at injection, we started around 55 at 130, 140 GeV. That's statistically consistent with the injection polarization. And then in this range, you can see this is 0 suppressed. So this is 35, 40%. So there's a significant loss, at least in the yellow beam polarization through this resonance here, and then at flat top 250 GeV, you can see that we lose about 10%, maybe a little more than 10% from injection to flat top energy. So you can see that if you think back at the beginning of the talk, I said the source gives you about 80% polarization. If you can maintain that for EIC, you will probably be able to deliver the 70% polarization that you want to work with. There's just one more thing that's kind of related to the Siberian snakes. That's the spin motion through this spin rotator. And it should be pretty obvious if you use this Siberian snake setup to rotate your spin direction or polarization direction from up to down. You can also use this if you know how to set your magnetic field values to have this up polarization direction, and then you rotate this where the vertical polarization is actually 0, and you have a longitudinal polarization. So this is essentially a variation of this Siberian snake that you use as a spin rotator to turn your transverse polarization into a longitudinal polarization around the experiments here.
Excuse me, I have a question. What makes it in this case we have a non-zero SX, while
that's
the spin snake we had.
Well, that's just being not quite as lucky, I guess. So, I mean, here you can see that if you wanted to, let's see if I can get this. So it depends on what the magnetic field strength is and how much of an excursion you can allow here, I guess. So you could, let's see if I can find a good point here. So you could use this setup to turn this vertical polarization into a negative sideways polarization, right? But at that point, you would still have something that has a slight vertical polarization. It has no longitudinal polarization. So it's really a question of how can you optimize the interplay between the three different components to make the one that you want the largest and the two other ones that you don't want the smallest.
So it's kind of a lucky coincidence that it is possible for the transverse direction to flip exactly without getting anything in the unwanted directions.
I don't think it's lucky coincidence. It's a question of optimization and how much work you actually put in. One funny thing in this context is that's really a lucky coincidence. Turns out if you reverse the currents in these spin rotators to turn the SY into an SZ, if you reverse the currents, it turned out you could turn an SY into negative SX. And then the other question also is, and I'm going to come back to this tomorrow. So this is a calculation or a simulation, right? At the end of the day, you really have to measure this. So you have to make sure that what you think this device does is actually what it does. So you have to make sure that you find a way to either measure this SZ or measure the remnants of SX and SY. Maybe in those another thing that happened on the last RIC run in 22, where one of the Siberian snakes and RIC actually failed. And it turned out, I think it was the third dipole here that failed. And there was a way to use, so there was a way to remove the second dipole. So you only were left with this partial snake with dipoles 1 and 4. And machine people were able to combine this with one of the spin rotators of the experiments to essentially create a full snake by combining two different devices in two different locations. Otherwise, last year would have been a complete disaster for one of the two polarized beams. Okay, I'm almost at the end. I just want to say one thing about synchrotron radiation. I don't know how much Cyprian talked about this for the electron beam, where it's very important, not only for potentially creating a beam polarization, but for the EIC is more a problem, which means that you have to re-inject more often. For proton beams, it's essentially not a problem, not an advantage, and that's because what I say here, the radiated power, which is essentially the strength of how fast the beam is polarized by this synchrotron radiation. I'm writing here it's e to the 4 divided by the radius of the accelerator. It's really the gamma here, so it goes with 1 over the mass. So the reason why this is nice or bad for the electrons is because they're very light. For the protons, they're very heavy. So even if we keep the particles in the ring for 8, sometimes even 12 hours, it doesn't make a difference in the depolarization. Okay, I'm just going to try to sum this up briefly and then leave you with a little food for thought. It's not really homework, but something for the discussion for after lunch. So the polarized beams at EIC, again, between 50 and 275 GeV energy. Each store is probably going to be similar to what we do at RIC right now, is on the order of 8 hours to maximize your maximize the efficiency of the luminosity and how fast the beams burn off. This might change depending on how efficient you actually run. It might be longer too. So I don't know. But this is a good starting point. One thing that I try to really emphasize that the beams are bunched and they will have alternating polarization directions. So the yellow here, you should always read on these slides as the proton beam. The blue for EIC is going to be the electron beam. So the bunch spacing between these bunches is going to be on the order of 10 nanoseconds. So we will have about close to 1,300 bunches in each ring where they collide with a rate of, okay, I'm gonna have to do this in my head right now. The collision rate should be on the order of 750 kilohertz at that point. So it's close to a megahertz, right? So that is something you should also consider. And then one thing that it's kind of a spoiler here, these alternating bunch polarization directions, I actually intended to reduce time-dependent systematic uncertainties. And you should forget this right now. This is something that you should think about. So for the electron ion collider, we want this absolute beam polarization measurement with a relative uncertainty delta P over P on the order of 1%, no more than that. So what do you think you should consider for polarimetry at EIC to really address all the questions that I tried to point out here? Like you have your source polarization and you want to go to flat top. What happens in between? How do you address this? The bunch itself has a size longitudinally and transversely. How could that potentially affect the beam polarization itself, thinking about the betatron oscillations and what might happen to particles that are further out compared to particles that are at the center of the bunch? And why do you think, or maybe you think that the bunch polarization pattern is important? What does that really mean in terms of reducing your systematic uncertainty? Okay. And the next slide has kind of the answers, but they're not online yet. So there's that. Thank you. Thank you.
Right, questions to Oleg.
Too much experiment.
That's the thing.
May I just know why the bunches in the proton and the electron beams? In the proton beam, they are kind of paired, whereas in the electron.
Well, that's just because I drew it that way. It doesn't have to be that way. It kind of goes back to this question, maybe. I don't know. You can think about this if you try to put this on a piece of paper or on a whiteboard. You have let me call this a bunch trade now, right? So you have these 1,200 bunches that come in here. So you have 1,200 bunches that go around this way. And then you have 1,200 bunches that come from here and that go this way. At this location, if bunch 1 collides with bunch 1, it means that bunch 2 will collide with bunch 2. And that's how this goes for eternity. You will never have bunch 1 collide with bunch 2 if bunch 1 once collided with bunch 1. So you will always have this one collide with that and this one collide with that. So if you had the same pattern here and there, you would have, let me say, so if this one collided with the same pattern there, you would have down collide with down, up with up, down with down, up with up, down with up, down with down, up with up. You would never have, and that's more important for helicity asymmetries, you would never have where down collides with up. So you somehow need to break that symmetry if you want all possible combinations.
Yeah, so at the end, you mentioned that alternating polarization states in the beam will reduce time-dependent systematic uncertainties.
Yes.
So why?
Well, you tell me. I'm gonna answer it tomorrow,
Okay.
or maybe after lunch. I don't know. Yes, yeah.
We talked about these alternative patterns, so we are going to have monitoring what the polarization of both of the beams for each bunch crossing is.
Yes and no. So this pattern, you define I should say, this pattern you define in your source. You can tell the source, I want a positive polarization or I want a negative polarization. And I should also say that the way you fill this is not the way it actually sits on the rings. So if you remember from the source, it said a single bunch has a length of 300 microseconds, blah, blah, blah. You make one bunch, you put it in the ring. You make another bunch, you put it in the ring. It's not you have one bunch and then you produce it, the next one, the 10 nanoseconds after you produce one, you get it in there. You produce the next, you get it in there. So, but you know what the pattern should be. So you know what you want. You have to make sure that you get what you want also. And I'm going to talk about this tomorrow. It's one of the requirements. You need to be able to measure this bunch by bunch.
Control this 10 nanosecond bunch especially in.
Well, the bunch spacing itself really is directly related to my RF unit, the unit that accelerates my particles. So it has a specific frequency, and that it needs to be matched to the circumference of my ring, right? So I need to be at the same location, which is my RF unit, with respect to the phase in my RF unit, consistently in the same spot. So the RF unit in combination with the length of my closed orbit really tells me what the bunch spacing is. The different way you've got some room to play with that, but it's a pretty fixed value for the machine. And I can say for Rick right now, the bunch spacing is a little over 100 nanoseconds. For EIC, we want the 10 nanoseconds to get the high luminosities. Otherwise, it won't work. Or otherwise, it's not going to be worth it.
This is intrinsic and imperfection resonance is specific for proton beam polarimetry.
It's the same for every polarized beam, but you should note it depends on this gamma factor. So it depends on your energy and the mass in that case, right?
But we never considered this for the electron beam.
Well, the electron beam for the EIC is very different because it has this rapid cycling synchrotron. And there's one detail that you might miss when talked about in most cases. They use this rapid cycling synchrotron to specifically avoid any resonances. If they didn't have this smart setup, they would have to deal with that too.
So why can't they use the same for proton beam?
Because the energy range is much larger. So the rapid cycling synchrotron is based on this fixed field gradient magnet, right? So it has these different levels where you essentially go through each ring just once. If you wanted to do that for the proton beam, so and the RF unit, say, I'm just making this up right now, but if you have an 18 GeV beam, the RF unit might give you 3 GeV per turn, right? So you only need 6 levels to get from 0 to 18 GeV. If you do that for the proton beams, you would have to get from 20 to say 250. That's 230 GeV divided by 3. That means you would have to have 80 separate levels for your fixed field gradient. So yeah, it's too much. Okay,
All right.
else?
Questions? Let's thank Oleg once. Lunch at 1. Okay, let's stick to the schedule in order to make sure that we can get it out.
Yeah, so 1 o'clock, we'll have discussion mixed with coffee break. Again, coffee is over there, but you're welcome to use this room if you keep it clean. And then 2 o'clock, we'll start the tutorial. So we'll move that up a little bit. Okay, 1 o'clock, 2 o'clock. Have a good lunch. Nice.
Let's go faster.
Yeah.
I don't like.